have a new transcriptome and you want to annotate it. By itself, it's just a set of nucleic acid sequences. Our primary goal in annotation is extrapolation. We're trying to map what we find in the new transcriptome to what we already know. And as it says here, most of what we know is protein coding. That's the information that we're best at. And in that light, our principal tool for doing this sort of work is using a protein alignment to known reliable resources, as it says. We've been making protein alignments for over 50 years. These alignments have shown us that if we can match up the sequences across different organisms, we can have a good guess at what the role of that gene is in the new organism, the new transcriptome that you're working with. You can work with general resources such as Swissprot, or you can go after the complete proteome of a related model organism such as fly or zebrafish or mouse, and you'll gain great information. If you can't get a good protein match, we still have tools, and we'll show you those quickly here, that can let us identify domains, the functional pieces that get put together in a modular way across different proteins. Even if you can't get a good domain match, there are still additional computational tools available that will search for things like transmembrane proteins, signal peptides, things that have a clear statistical pattern that programmers, computational biologists, have studied and developed tools for predicting. So if we look at this all graphically, we start with our new unannotated transcriptome. We run it frequently through a program called Transdecoder. There are alternatives to this, but Transdecoder is the most popular that will predict the proteins associated with this new transcriptome. It does this based upon finding long open reading frames. It also does some statistical analysis to say which of these are more likely to actually be consistent with what we believe about the protein coding sequences and probabilities and such of this organism. From there, we will align it, as said in the last slide, to new proteins. From there, if it's a well-studied organism, we might already have ontology terms that allow us to use these alignments to the other proteins to gain information about ontological classification of these new genes. Again, if we don't have that, a little bit less information, but still valuable, is if we can use a tool like Hammer to search for known protein family, PFAM domains. If we can't get that, we can go after the pattern searches, such as the transmembrane domains with TMHMM or signal proteins. There are other tools of this nature. Once all of these are collected, we can then put them into a database that allows us to look these things up. Trinitate is the most commonly used tool for this. All of this that I'm showing you is dependent at this point upon the quality of the predictions and upon the validity of the predictions of this. And there are reasons why this might fail. And so as a result, we can actually mirror this entire process and do all the same work at the transcript level. It is possible to do the 6-frame translations on all of these transcripts and search for all of these same tools, and pretty much all of these tools have the capacity to work at the transcriptome level as opposed to the predicted protein. If you do this, the work is computationally faster. Once the proteins have been predicted, it's a faster alignment and it's more easily interpreted. On the other hand, if you have limitations, whether it's through sequencing errors or unusual proteins that use specific coding sequences, you get the computationally slower but less subject to limitation version of each of these. And so finally, once all this is done, it's put into a transcriptome database and you have your information for working with going forward.